We are going to get started on time this morning. It's 10:15 and you're in room 6. Appreciate you all joining us for a cool project, the Alligator River Bridge replacement. Just a couple of quick notes before I turn it over to these guys. You've got a great list of speakers here this morning. At the end, we'll have a Q&A, and I'll also put up a QR code on the screen, as well as one in the back of the room, in case you missed the one on the screen. But thanks for joining us, and I will turn it over to you.
Good morning, everyone. So we're here to talk about the Alligator River Bridge replacement, TIP project HB0001. I see there's a couple empty seats, and that's because we're competing with Dr. Hummer, and he always has standing room only, so we get the overflow. So for those of you who don't know me, my name is John Conforti. I'm a senior project manager with the Project Management Unit in NCDOT PMU. I'm here today with Craig Young from Three Oaks Engineering, Charles Smith from our DOT Hydraulics Unit, David Stutz from our Structures Management Unit, Andrew Derda from our Geotechnical Unit, and last but not least, our own Randy Midget, our Division I Construction Engineer. So we could basically talk all day long about this project and not even cover half of the facets of the project. So we're going to do our best to kind of walk you through the highlights, and then we'll have a Q&A session at the end. So a little bit of background. This bridge was originally part of TIP project R2544 and R2545, and that was the proposed widening of US 64 from Columbia to Mans Harbor, which was a distance of about 27 miles. That project, of course, did include the replacement of the Lindsay C. Warren Bridge, which kind of splits the project with Terrell County on one side and Dare on the other. The proposed widening of US 64 was a 4-lane median divided highway. The new bridge, of course, was going to be a 4-lane divided bridge. See the cross sections here. So, like I said, a little background. The P&E work, planning environmental work, started in 2007 and originally included the replacement of the bridge. This was a merger project. Draft EIS was signed in January 2012. Final EIS was completed and reviewed in late 2016, but was never signed. The project was kind of on again, off again due to funding. And the division expressed concerns with the bridge needing to be replaced due to the overall condition, the age, and the swing span, which had a history of breaking down, and Craig will probably touch more on that later. And I lost my mouse. Oh, okay, but I mean for the over here. It's not working.
All right.
Nope.
There it
There
goes.
we go. Wouldn't be a presentation if we didn't have technical difficulties. So the original plan was to finish and sign the final EIS and then to complete the ROD. And then what we were going to do is obtain a phase permit from the Corps of Engineers and then phase construct the bridge if money became available to do so. But there were some issues there. With the time that it would take to complete those major documents would probably take a couple of years. And there were also risks associated with the project because the proposed widening, at least on the Dare County side, was going through the wildlife refuge. So with the potential risk of litigation and whatnot, the bridge basically would have been held captive with those two larger projects, which were unfunded and weren't going anywhere anyway. So I had kind of floated the idea with Jerry Jennings, who was the Division I engineer at the time, about pulling the bridge project out as a standalone project, since it was a bridge replacement, do a CE on the bridge, and hopefully come up with funding at a point later in time. So we started looking at doing a categorical exclusion in 2020, and in December 2020 we started having more detailed discussions to prepare a CE and replace the bridge and approaches utilizing the LEDPA location for the parent project. The bridge would be a 2-lane bridge, of course not a 4. It would have its own TIP number, and would include the bridge on new location and the approaches, which would tie back into US 64. And with that, I'll turn it over to Craig.
Thanks, John. All right, so as John mentioned, this project started as a larger widening project with a bridge replacement under merger. And as also John mentioned, I think it was late 2020, early 2021, when the decision was made to refine that down to just a bridge replacement here. Kind of run through the timeline, or at least the agenda that I'm going to cover here. We've already touched on the larger project. We'll speak a little bit now about the smaller, or the individual bridge replacement. That was HB 0001. A lot of zeros in there. Got tired of saying that a lot of times on project meetings. We'll go through some of the existing constraints that we were dealing with. This project, the HB project, was merger, stayed in merger. We had a range of alternatives that we considered. We actually built off of the alternatives that came out of that larger parent project that John mentioned. And then we'll discuss the selection of the LEDPA, or the preferred alternative, and then touch on just some of the kind of the milestones to getting to that completed environmental document. So the 106 MOA, and ultimately the federal highway categorical exclusion. All right, so there's the existing bridge, and with that, in February of 21, project team was awarded this project, or assigned this project, by PMU. Phone rang, John Conforti on the other end, asked me if I had availability to take on a bridge replacement project in the eastern part of the state, and I unknowingly agreed to something that took the next 4 years of my life. So DOT was the lead here. We had a great team that was assembled. Three Oaks was the prime consultant. We had Majeski and Masters that did the structure design. Summit Design Engineering did the roadway, drainage, and erosion control and permitting, or permit drawings. WSP, at the time it was Wood, before they were acquired by WSP, but they did the geoenvironmental foundation design. And then Volkert is handling the utility coordination and utility design for the project. All right. That was the key when John called me, was here's the project. It's got an accelerated schedule. It's merger. It's got Section 7 consultation with some of the endangered species in the area. Oh, it's got Section 106 MOA because the bridge is historic. And we're going to do it as a Type 3 CE. But wait, there's more. All right. We need it by August of 21, because I believe I asked which year here when John said
So
that.
just a little background on that. And like I said, we started looking at doing the CE at the end of 2020. So right around, sometime around Christmas at that time, Chris Werner, who was our previous director of technical services, called me and said, how long do you think it'll take you to get the CE done, to get the planning done on Alligator River Bridge? So I thought about it, and I knew they wanted it fast, and I said, well, probably about 12 months. I said, that might be pushing it, but 12 months seemed reasonable, December of that following year. And he said, well, do you think he can get done in April? It's like, I said, you got to be kidding. There's no way. So, of course, as any negotiation goes, I was looking at the 12th month. He said the 4th month, so we settled on the 8th, which is how we got to August. So that's pretty much
Thanks, John. Thanks, John. All right, so the clock is ticking, right? We're in February here. And that was my response to John when he told me August, right? You got to be kidding me. But we'll do our best. All right, into the existing constraints. So with this map here, this is kind of our environmental features map that we developed early on. You can see the existing bridge alignment is that thin blue line crossing the river to the south, and then our new bridge alignment is the red line at the top. Pay no attention to the colors that are on there right now. I'm going to kind of fill this in and show you some of the constraints that we had. On the right side of the screen is the Dare County side. The county line is right in the middle of the bridge itself. So on the Dare County side, we had the Alligator River Wildlife, or National Wildlife Refuge, which is that yellow shaded polygon. On the opposing side of the river, on the Terrell County side, we had a series of public lands. We had the Alligator River game land and the Palmetto Pear Tree Preserve, which the Palmetto Pear Tree Preserve had a known population of red cockaded woodpecker there. And then right below the bridge on the left side of the screen, we had a small little site called, this is my favorite one, this was called the Whammy site, which was the Waterfront Access Marine Industry Fund site. It's a CAMA site for local watermen, crabbing, fishing, to use as an access point. There's a dock and a boat ramp there. So that's that tiny little blue polygon. In addition to that, along the shorelines, we had CAMA shorelines. Those were outstanding resource waters, CAMA estuarine, and ocean system area of environmental concerns. And we also had anadromous, I always get that wrong, anadromous fish spawning waters, all throughout the entire project area, right? In addition to that, we had an in-water work moratorium that spanned from July 15th to September 30th for the entire project area, and from February 15th to June 30th for the deep water channel, which was 1,000 feet on either side of the navigation channel. So you got just a couple months out there, Randy, to be in the water, to drive piles and build that bridge before you got to be out of it. Exactly, in the worst time of the year, the winter, when it's not fun to be out there. The last thing we had that was a constraint was the existing bridge itself. As I mentioned earlier, it was eligible for listing in the National Register of Historic Places. All right. For the alternatives that we considered, we kind of started with the range of alternatives that came out of that larger EIS study. You can see the map here. I kind of refer to this if the older folks in the room like myself that remember Ted Devens from back in the day. He was the project manager for that R44, 44, and 45 project, and I refer to this as the Dr. Devens spaghetti map because he just had lines going all over the place, but for good reason. With all those constraints out there, they were really having to look at all the different ranges of alternatives and combinations. So that was our starting point, and it was my charge to kind of take what Ted had developed and figure out how to refine that down and hopefully land the same selected LEDPA that came out of that EIS effort, and then present that to the merger team over the span of 6 months to get to a new LEDPA. So that was the map that we showed earlier. Again, just more of a refinement of those alignments. There were a couple alignments to the south of the existing bridge that were dropped in the EIS, and we had to kind of reaffirm that as part of this because we knew that the merger team and the agencies were going to ask about that option. Because of some of those constraints, the southern alignments didn't really work. We ended up impacting those public game lands and the wildlife refuge with the southern alignments. All right, so getting to the selection of the LEDPA here. That was our merger 2 and 2A meeting map that we brought to the merger meeting. We really focused on the roadway approaches because the bridge itself, if you think about it, the bridge could connect to any one of those points on either side of the water there. So it was really just trying to figure out where those impacts or where we were going to thread that needle on the land-based side of things. That was the table that was used in selection of LEDPA, all the colored alternatives along the top with the HB0001 red column at the far end. That was ultimately our selected LEDPA. It did end up being similar to what came out of the EIS. It also ended up being the least environmentally damaging. When you look at the numbers there, it had the least amount of impacts to those constraints that we talked about earlier. And this is just the map that we used in the CE that showed that alignment, the roadway approaches, and the new bridge alignment to the north of the existing bridge. You'll see on these maps here, there is a label for a proposed wildlife crossing. That was a concern that came out of the merger team. It was also something that was included in the larger parent project. There are large 53-inch by 41-inch arch pipes on each approach, as well as wildlife fencing along the corridor. Particularly on the Dare County side, you've got black bear, red wolf population. I think it's the only population in North Carolina. as well as some smaller mammals and reptiles that cross that road. If you've ever been through that section, it's pretty undeveloped through there, and you will occasionally see black bear crossing 64. And that's the Dare County side there. You can kind of see, it's hard to see with the colors up there, but that threading the needle, we really had a very small area to kind of land the bridge on the Dare County side that stayed out of the wildlife refuge. And we were able to do that with the alignment between the work that Summit did for the roadway alignments and the bridge alignment that Majeski was working on. Really kept us just skirting the edge of the wildlife refuge. All right, so as part of our work in the planning stage, because of those endangered species populations, we did have to do Section 7 consultation with Fish and Wildlife Service. You can see the partner agencies there, and that Section 7 consultation, and it was for the RCW on the Palmetto Pear Tree Preserve. That was signed in November, so actually after the signature of the CE, we received Fish and Wildlife's biological opinion of I think it was a no jeopardy call on the RCW. And I lost my mouse. All right. In addition, we had a lot of coordination with SHPO on Section 106 for the bridge. It resulted in the development of the Memorandum of Agreement. And pay close attention to the yellow highlight there. As part of that MOA, there were some stipulations. One was photo recordation of the existing bridge. I believe Division flew the bridge with a drone to take pictures and video. The plan is to tear down the existing bridge after the new bridge is built. And then in particular, Renee wanted to see 4 standalone decorative panels and their support structures in each of the 4 quadrants of the new bridge. And I'll show you something at the end here of kind of where that ended up. But her idea was to have these panels represent some of the animals that are protected and are in those public lands and in the wildlife refuge there. All right. The other thing to pay close attention to is that date and time. So we signed the MOA August 31st, which was 6 months from February, at 4:38 p.m. Federal Highway. I got on a call when we got that MOA. I see Colin sitting out there. I think Colin, John, and I got on a phone call. We had the signed MOA, and we quickly uploaded the CE to DocuSign and circulated that. Type 3 CE, wait for it. Signed on the 31st, same day, at 5:32 p.m. So we came in just under the wire. I think we missed it by 2 minutes there. But we made it. We made it in 6 months, believe it or not. Takeaways here for me, we only made that deadline or that goal through communication. We held bi-weekly meetings. Those were key to delivering on the schedule and on budget. And it really was a team effort all around, both on the department side and the consultant side. I think everybody understood their responsibilities. We understood the accelerated project schedule. Lots of emails, texts, team chats, everything that really helped deliver that project. Again, there's your communication. That was the last merger meeting picture, by the way. Actually, the merger meetings went really well. So merger meetings, March 21, CP1. CP2, 2A was April. CP3, 4A was June. So you see, we just rolled right through those. And it was really reaffirming the work that Ted had done previously, and just making sure that what we were doing for this project was still valid with the merger team. I mentioned the biweekly status meetings. To this day, we're still doing those. We'll probably be wrapping those up next month, but we've done those ever since probably February, March of 21. We did hold a constructability review meeting early on. Randy will probably talk a little bit about the contracting method here, but that, I think, was very helpful, at least for a planner all my life, to kind of sit down. We were on site there. They brought in a couple construction contractors and just had an early conversation with some of the challenges and constructability issues that we were probably going to run up against. And I think that really helped the department understand those issues and help steer the design team with the foundation and structure design. We had a couple different changes along the way that I think probably started at that constructability review meeting. And then all the communication, emails, calls, Teams, chats, text, everything. And really, we succeeded in delivering that document and designs because of the constant communication. And that was team effort all around. All right, so these last two slides, going back to those decorative statues, I think this is just, to me, this is the cool part of the cool project here. There's a local artist in Wake Forest that has been brought on board called Peter Rocchio, or Rocchio Designs. He developed on the left side are mock-ups. You can kind of see the clear acrylic person standing next to those. But those four animals, it's the black bear, the red cockaded woodpecker, red wolf, and the American alligator. Those are the four animals. There'll be one in each of the four quadrants of the new bridge. And then we went up in October of last year to visit Peter's shop in Wake Forest. They started cutting these panels. They're made out of Corten steel, which is the brown color, and the silver color is stainless steel. And they're layered. You can kind of see it on the red cockaded woodpecker. So it's these panels of steel that are layered to give it depth. They're about 10 to 15 feet tall, depending on which statue you're talking about, and they'll be mounted on a concrete pedestal that sits behind the guardrail on the roadway approaches. I'll show you a driver's perspective view here in just a second so that you'll see those sitting up above as you approach the bridge from each direction. That's kind of the driver's approach graphic that one of our, actually I think the contractor, I think Skanska put that together, just to make sure that we had set those pedestals high enough that the statues would be above the guardrail. So when you're driving 64 after the bridge is open and you see those panels or those decorative statues, you saw it here first. All right, and with that, I'm going to hand it over to Charles and let him get into the design details on the hydraulic side.
All right, as Craig said, I'm Charles Smith from Hydraulics Unit, and because the low chord elevation of this bridge was determined a little bit differently than what we normally do, I'm going to go through some aspects of ultimately arriving at what that was. There we go. All right, so we had several components that were added together to calculate the 16.5-foot low chord elevation. Now, most of the spans have a low chord elevation of 16.5 foot. The approach spans, about 16 out of the total number of spans, have a low chord elevation somewhat lower than that, just because of the reality of tying down to existing ground. That's very tough to do with a 16.5-foot low chord elevation without having right-of-way impacts and longer tie-down roadways and that sort of thing, which would violate some of the constraints that we had on the site. So within the green box, we have mean sea level. Everybody has to have a datum. You have to have a datum whenever you start this sort of thing. NAVD 88 is approximately substantially equivalent to mean sea level. And then on top of that, we added sea level rise that's projected to have occurred by the time we reach year 2100. And on our graphic, we have the water level, flat water elevation right there, which would be sea level rise plus mean sea elevation. To that, we added the 100-year storm surge. I'll get into how that was derived in a little bit on the next couple of slides. So storm surge is just that amount of water, that elevation of water that's added on top of mean sea level rise plus, or mean sea level plus sea level rise. And then we added waves on top of that because it wouldn't do to have waves crashing into the bridge deck. And that wave height was determined by modeling to be 8.1 feet. We added a foot of freeboard for good measure, as well as a 0.4 foot future wave height increase to account for increased intensity of storms in the future. Okay, so this graphic is from FHWA Hydraulic Engineering Circular 25. That is coastal engineering. That's their hydraulic engineering circular on coastal engineering. If you look at this chart down here, this table down here, 3.97 feet in year 2100 is the RCP 8.5 projection for sea level rise. And there's a number of different studies and whatnot represented on this graph. Bottom line is that our 4-foot elevation is what is recommended for major structures in high-risk areas by HEC 25. What is RCP 8.5? That is representative concentration pathway. So all that really means there's a number of climate change scenarios. 4.5 is one of them, 8.5 is another. And what that ultimately means is that there are 8.5 watts under this scenario that are retained per square meter of Earth compared to those watts escaping the atmosphere. So there's an imbalance or a delta of 8.5 watts retained by the atmosphere due to carbon. All right, so that accounts for our 4 foot sea level rise by 2100. There we go. Okay, storm surge, 3 foot is what we arrived at, and Mike modeling was done to arrive at sea level or at storm surge induced by hurricanes. In this graphic, you can see a wind field and barometric pressure field in the blue. The highest concentration of wind is blue. This would be a modeled hurricane, and as you go out from the center of the hurricane, the winds get less and less intense. So there were a total of 68 hurricanes that were modeled in the Mike software, and they had various tracks across the bridge throughout the area. The bridge, you might note, is at the tip of that arrow. Another thing to point out on this graphic is that there is a varying density mesh that is gray. Oregon Inlet's right about here, the bridge is right about here, Corolla's up here, so on and so forth. That is a finite element mesh. Typically, you hear that in the context of structural engineering, but in this case, we're using it for water. And that is just a mesh of finite elements that are individually solved at their edges to determine velocity, shear, water depth, that sort of thing. So that's the type of modeling that was done. It's a little more complicated than HEC-RAS 1D. So as you can see that the mesh gets more and more dense close to the bridge, so we have greater and greater clarity or greater and greater granularity near the bridge to extract more detailed information from the model. Okay, so what are our inputs? The wind fields, barometric pressure is also an input, and bathymetry, including the 4 foot of sea level rise, is also an input. And in this chart, we used, or not we, the Moffitt-Nichol wrote the report. Moffitt-Nichol Coastal Engineering Department used an extreme value analysis to determine our 3 foot of storm surge for the 100-year storm. I think my last statistics class was in 1997, so I'm not going to try to go into what an extreme value analysis is, but it's a way to plot model results along a curve and extrapolate out to different recurrence interval storms. Okay, wave height. Wave height is another component that was added to a variety of components to arrive at our 16.5 foot low chord elevation. Coastal engineers have many, many different types of waves. There are numerous definitions of what a wave is. This is called a Rayleigh distribution, spelled like Raleigh, but pronounced Rayleigh. You have, of course, your mode, median, and mean. The mode is at the top of the curve. Significant wave height is a type of wave definition that is the average of the greatest 1/3 of waves, and the maximum wave height is about double. Really, it's 1.86, but who's counting? It's approximately double significant wave height. So to arrive at the 8.1 feet, we being Moffitt-Nichol, calculated significant wave height, doubled it, and then that ended up being 8.1 feet. And that was taken at location EO2. These are just locations along the bridge. I mentioned earlier the density of the mesh on the previous slide allowed us to have pretty good granularity, pretty good detail in the vicinity of the bridge and extract data from the model at various locations along it, and EO2 happened to be the highest 100-year elevation for wave height. Over here, wave height, the 8.1 foot of wave height is measured from flat water, so flat water is going to be sea level rise plus storm surge, and that is in the red. That is the arrow within the red box. Okay, so that's how we arrived at the 16.1 foot low chord elevation, so that well into the future, into 2100, for a 100-year storm, for a 100-year hurricane, our hope is, our prediction is that waves during a hurricane would not reach the superstructure, the low chord of the superstructure. So we also had to do scour calculations a little bit differently than we normally do for a bridge, say in the Piedmont or in the mountains, because this is a coastal environment. We did not consider any contraction scour. Contraction scour is when you have a contraction in flow, So if this is a plan view of the bridge and we had abutments that went way out into the Alligator River on either side, then we would have a flow contraction as water squeezed its way through the bridge opening. We don't have that in this case. There are actually fewer bents in the water than for the existing bridge, so we did not account for contraction scour. Over time, there's been an aggradation and degradation of the bottom elevation of about 2 to 4 feet based on bridge inspection reports over the period of history that we have bridge inspection reports for. So 3 foot of general scour was used, anticipating a continued variation of the bottom elevation of 2 to 4 feet just based on day-to-day scour and currents and whatnot. Local scour was determined, and local scours around the piers. That's around a column sticking into the mud at the bottom elevation, or at the bed elevation. So local scour around the piers is based on FDOT. FDOT has a pretty good program that's also used in HEC 18 for determining scour of coastal bridges. I think they're probably the leading authority on coastal bridge scour. So that's their method is what we went with, and the FDOT scour calculator was used with inputs from the Mike hydrodynamic model, which is the finite element analysis model for water that I mentioned a couple of slides ago. Okay, so this is the navigational span right under the center of the bridge, 65 foot of clearance. This is a screenshot of our BSR bridge survey report, which some of you may have seen. It's basically a profile of the bridge at the center span where the navigational span is. These magenta lines depict scour. Our little bit of scour here is the 3 foot scour that I talked about a minute ago, the aggradation and degradation, and then this is our local scour or pier scour determined using the FDOT equations. And for a 500 year, I can't read that, I think it's 25.4 foot of scour at each pier, so that's added onto the 3 foot for a total scour of 27 point something feet. So of course the pilings have to be set at a depth that's low enough to continue to bear the weight of the bridge plus traffic and account for scour down to that elevation. And the scour was calculated at each bent throughout the array of bents on the project. There's an array of pile types, an array of compound piles, which is a large cylinder coming down to a pile cap underwater or at the water elevation, and then a number of smaller driven piles beneath that cap is cast onto. So the FDOT method of scour calculation accounts for that. And that's really about it. So I'll pass it on to David. You wanna hold the mic, or-
Thank you, Charles. Sorry, there were 2 emails about what we were wearing today. The first one said we're going to dress up in costumes. The second one I did not get. So, my name's David Stutz. I'm a project engineer with Structures Management. I just want to kind of run through some of the things that Structures did to contribute to this amazing project. What we did, wrong button, this way. First thing we did was kind of set up a contract to get a navigation report. Majeski and Masters helped us out with that. We got that done in September 2021. The current navigation channel is 2 100-foot spans, like you see in the picture there. The Intracoastal Waterway is 120 feet wide. The navigation report kind of looked back at records of what kind of vessels were passing through there through January 2019 to December 2020. And during that period, they had 10,157 vessel passages through that bridge. And that involved 7,231 openings. That's about 20 times per day. So the conclusion was that this kind of helped feed the information that we needed to sort of what size opening did we want for the fixed span. And we determined that providing 140-foot horizontal, 65-foot vertical met all the requirements from the Corps of Engineers and the Intracoastal Waterway. So bridge economics. You got a bridge that was rehabbed in 2019 for $17 million. It'll be required again in the next 7. Oh, wait, I had AI help me out with these slides. That's telling me 5 now. So cost alternatives, the typical section, the bridge width for a 3.2 mile bridge. I'm going to call out any of you guys that have calculators for brains here. This is your time to shine. If you got 3.2 miles of bridge, right, 16,000 feet, all right. If you got a bridge cost of 185, oh, sorry, AI corrected me again. The cost is now $220 per square foot. You got $3.72 million per foot of bridge width. So every time you want to add a foot of width to that shoulder for spread or an extra travel lane for capacity, yeah. So the original bridge width was 78 feet. We got that down to the 42.7 that we're planning for now with the two-lane bridge. Resiliency, that something that Charles was talking about in his slides, the freeboard height. We were looking at an additional 4-foot height to handle the sea level rise. And so we helped determine and estimate the cost of that. If you're adding 4-foot height for piles that are about $200,000 per foot for the entire bridge length, then you're only adding about $800,000 to the total bridge cost. So it was doable. And the preliminary estimates, back when this was a bid build project, it was a total of $270 million total construction, and $165 million of that was the bridge cost. We also helped out with coordinating the U.S. Coast Guard permit drawings. Again, Majeski and Masters helped develop these permit drawings you see here with a location sketch, with the navigation spans showing the vertical and horizontal clearance, the access bridge and the temporary work bridge that we were going to use. The permit was issued October 30th, 2024. And then another thing we were kind of helping out with coordinating is the service life. You know, the bridges you see here is the previous Bonner Bridge and the new Bass Knight Bridge. Bass Knight was developed for a 100-year service life. You know, typically we do a 70-year bridge life, but let's put a little extra into this, so it'll, you know, it's going to be out there a while. 100-year service life for a marine coastal environment. We opted to do some glass fiber reinforced polymer to replace the reinforcing steel in the substructure elements. And the other thing we did was develop a foundation, sort of a feasibility study. As you see in this geotechnical diagram, they're showing that yellow layer is kind of a dense sand. And the existing bridge was able to establish their pile foundation on top of that layer. But now we're doing longer spans, we're doing heavier loads. This was a question: can we still establish bearing on that layer? And nobody was really certain. It came up in the constructability meeting. We were, you know, sort of balancing the constructability effects of doing piles versus drilled shafts. You know, you got a moratorium, so drilled shafts you can only drill your shafts in the during the outside of the moratorium. So what we had was kind of had a third party look into this and help us determine, you know, what kind of resistance can we get out of that layer. And ICE developed the foundation feasibility study. We had them looked at the lateral stability of the piles, the settlement in different areas of the bridge, the pile axial analysis and the drivability. Also looking into the potential test pile program and what we would want to see out of that. And a drilled shaft analysis to let us know the benefits of doing drilled shafts versus piles. And that's a good segue into Andrew's presentation on the foundation design.
Hello, I am Andrew Durda with the Geotechnical Design Unit, and this project presented us with some pretty unique challenges, so I'll just walk through a few of those today. As David had just mentioned, one of our biggest challenges was being able to hang the piles in that upper very dense sand layer. We needed to decide if we would be able to hang the piles there or drive through it to the lower sand layer, which would be about 150 feet down. Would the lateral stability be able to be supported in that upper sand layer? And what would the settlement of the presence of that soft clay layer right underneath those piles look like? Obviously, the moratoriums gave us a very short investigation window, especially for a project of this size. We would only be able to drill between February and October, and this led to limited sampling and testing performed. This is just a picture of the stratigraphy of the soils for this project. We were consistently finding clay layers, which are those two pink layers that you see, in between two sand layers. And that middle green layer is what we were looking at trying to hang the piles in. So we decided that we needed to go CMGC. This allowed us to create a test pile program. Let us try out a few different hammers, see the results that we were getting for the drivability, see what kind of capacity we'd be able to get from these piles. And it also gave us more time for investigation, let us go out, do more SPTs and CPTs, as well as collect more samples, which helped us be able to determine the settlement that we would expect from this project. These are just some pictures of the hammers that we used. We used 2 diesel hammers and 1 hydraulic hammer. That's the sampling and SPT testing. In the initial timeline, we started the field investigation in February of 2024. The test pile program was originally supposed to start right around then, didn't actually start till May of 2024, and we were done with both the investigation and the pile program by July. This is us hanging up the piles to get ready to drive them for the test pile program. We drove 15 piles. And what we learned is that we would not be able to drive through that upper sand layer. We reached blow counts of 180 blows per foot in 5 of the 11 locations, which is on the upper limit of what we allow for drivability. Our end of drive capacities were all above 2,000, with many of them being above 3,000 kips, which gave us ample capacity. And if we were looking to lower the blows per foot, we started to get concerned about the compression stresses in driving the pile with a larger hammer. But at the same time, we're worried about the fatigue of piles getting hit 180 plus times. And due to the extended testing that we were able to do, we did some high pressure triaxial tests and were able to determine that the OCR of that soft clay layer was greater than 1.5. So while there would be some settlement, it wouldn't be an issue for the structure. So the outcome we landed on was we would be able to hang the piles high. We found we were getting ample capacity. We found lateral stability to be satisfactory. And this allowed us to shorten the piles. It's a lot easier to stand and drive the shorter piles. It's a much shorter schedule. We initially looked at doing pile excavation through the very dense sand layer, and we found that it was going to take about 4 days per pile between doing excavation, driving, and then pulling the casing. So not having to do pile excavation, not even including getting rid of all the spoils, saved a significant amount of time. And it reduced a lot of cost. We were able to eliminate just under 100,000 linear feet of pile length by being able to hang the piles up in that sand layer. So it was a significant savings there. And the rate of return, the lab testing cost us about $1.1 million. The test pile program was about 13.6, and we saved about $80 million and was able to shorten the schedule. That's all I have, and I will turn it over to Randy.
Gotta look, see how much time y'all got till lunch. And I do not want to be in the way of that. I'm Randy Midget. As earlier said, I'm the Division Construction Engineer for Division 1. Division 1 is a wonderful place. If you haven't been there, please come and take a look, visit us sometime. I like to call Division 1 the land of really cool bridges. We have most of the biggest, longest bridges in the state. And I was just thinking about it as I was sitting there earlier, waiting for my turn to go. I started work with DOT 31 years ago next week. And my very first day was on the Wright Memorial Bridge sister spans. And that was the very first project. That was the new 2 lanes that was being built across Currituck Sound at Wright Memorial. And that one's bridge is 3 miles long, 2.8, something like that. I can't remember. And through the course of that 30 years and finishing, but I think we'll be finishing up here with Alligator, another long bridge. You know, I've had the wonderful experience of being associated with just about every long bridge that's been built in the division. There's been some really cool projects. And this is one of them. This was a really interesting problem. It was a technical problem, especially from a foundation standpoint. And what I'm going to do today is I'm going to talk to you a little bit about the change. This project was originally slated to be design, bid, build. We had the time. We didn't at the time we thought we didn't know whether we were going to have the funding, so we didn't know when we were going to build. So we're like, let's take the time. Let's do the design, then we'll put it out to bid, and then we'll build it. You know, under a traditional delivery method. As you saw earlier, things kind of kept speeding up during the life of this project, and once we got about the 60% mark, Lord. Okay. All right, now I got my buttons right. Once we got about to the 60% mark, we were working, as Andrew said, we were, especially in the foundation aspects, we were working it off of very limited data. And as engineers, we make all of our decisions based on data. We're data-driven decision makers. We had that very short, narrow window to get most of the geotechnical work done. We weren't able to get a ton of borings. Some of the consolidation borings on that middle layer, some of our samples were damaged. We weren't able to get really good information, but we had to proceed based on the amount of data that we had. And at this point, we were pushing 2 different options. This was right after the constructability meeting that we brought in 2 contractors. And constructability meetings are great. They give you a lot of good ideas, but you're never going to have a contractor when he's got another contractor in the room say that I can't do that or that's not good. They all say, oh, yeah, we can do that. We can do that. But what you have to do is you have to read between the lines and go, yeah, we can do that, but it's going to be really expensive. So the division, you know, when we're pushing this 60% design, this is where we were. We had a 2.84 mile drill shafts was one of the 2 foundation options being put forward in the plans. We had a 2.84 mile body of water, very rough, tough place to work. We were going to have 360 foot shafts that were deep, and they were 5-foot diameter. It was going to take 37,000 cubic yards of spoil to excavate out of those shafts. Okay, now how are we going to handle that out on a 3.5 mile water body? We got to get it back to shore. We can't just throw it overboard. And if you know anything about the area, it's wetlands for miles and miles and miles on either way. So soil disposal was going to be a problem. We knew we'd have to have slurry to drill that deep. Slurry handling, slurry management was going to be a problem. The amount of flotilla of equipment that it was going to take to drill these shafts out on barges and not spill any. Remember, we can't drop this mess in the water or we get permit violations. It was very concerning. And the drill shaft option was also going to require 42,000 cubic yards of concrete just to fill those shafts. Again, we're 2.84 miles to get out to the shafts. The alignment that they showed you earlier, we can't feed it from the existing bridge. We got to put it on a barge and get it out there. And, you know, when you're doing drill shafts, you expect that concrete delivery to be continuous, consistent, and you can't have any breaks. The other option we were looking at and we were putting through design was pre-drilling of the pile, which is essentially a precast drill shaft, because we didn't think the drivability analysis was showing that we couldn't drive through the upper layer. We were trying to get down to that minus 140. It was going to make these concrete piles 150 foot long. And now think about it. These are 36-inch square piles. They're the size of a residential refrigerator, and they're going to be 15 stories tall. We got to pick them up, stand them up, and drive them in the ground. So it's going to be, you know, pretty difficult to do. We would have to case it to pre-excavate it. We weren't sure whether we were even going to have to use slurry to get through because we weren't sure if we were going to have to dig all the way down to close to minus 150, or we could stop excavating at the upper layer as soon as we penetrated the hard layer. And we had about 696 piles to drill. So it was looking like a lot of effort to get the foundations in on this job. Again, we had spoils handling. It wasn't quite the 37,000 cubic yard, but spoils management was still going to be a problem. And then we were also having to look at backfilling the annular space after we stood that pile up and put it in the hole. Although later we were able to get rid of that, thankfully. But it was going to be really slow construction. So then this was, around June of 22 when we're pushing between 60 and 90% of design. In January 23, the department received the mega grant for the project from FHWA. That was $100 million. Well, $100 million will jumpstart a project pretty quickly. Not that that the department had the money for the rest of the project, but we're not going to turn down $100 million. So Raleigh got pretty busy trying to find the money for the rest of the project to get it going. And at the same time, we were getting a little concerned in the division that this was going to be a risky project because both of these methods had a lot of unknowns. And whenever you're asking a contractor to bid, a lot of unknowns, it's going to be very expensive. So we started thinking and looking, what are our, the benefit was we didn't have to cast those piles out there on the water. So we started thinking, how can we reduce the risk and maybe bring this project in a little better and not have these huge claims at the end of the job that we had been having on a lot of our other large bridges. And at the time, back in 2022, we only had 3 methods that were approved. The design bid build, which was the path we were on. The design build option, which the department had a lot of experience with and the division had experience with. But the problem with design build was we already had a really good team. We had a great team of designers. Everybody that was involved in the project was working together. I mean, from getting to sea in 6 months to moving through design. To go to design build, we'd have had to throw the baby out with the bathwater. And we didn't want to do that. That just was unproductive for a project at this stage. And the CMGC, we started hearing about, at the time, the state was allowed by legislature to experiment with 5 projects. They had started experimenting on a few of the mega projects, but we hadn't really done any of the highway projects with CMGC. But one of the things we liked about CMGC was we were able to bring on a contractor as an independent third party to give us advice, allow us to give us a little more expertise on pricing and what things really cost. As engineers, when you get down to doing cost estimates, I can do a cost estimate, but I'm not doing it at the level that a contractor is. So we thought that might be a really good idea. And my division engineer, he said, Randy, he said, I think that's a good idea too. He said, put down some bullet points that I can take to Raleigh about, how we can help improve this project. I think I wrote 4 pages of stuff, and one of which was to switch the project to CMGC because we felt like that would reduce the risk, or at least get the risk a little bit shared a little more equitably between the contractor and the department. It would give us assistance in making better decisions about the foundation methods because they were the biggest unknown in the project. And I like this slide. And, we took a pause and we kind of turned the ship by moving the project away from design bid build to CMGC. And that cost money and it cost a little bit of time. But this slide, I stole it, by the way. I stole it out of a Federal Highways alternative delivery workshop that I went to not too long ago. And it has a lot of good food for thought. A more accurate representation of the scope can result in a more reliable cost, which benefits the owner, the contractor, and most importantly, creates a more efficient investment of the tax dollar. So what we decided was to spend a little bit more money in project development and hope that it would save us some time down the road. We were able in the spring of 2023 to get approval from the chief's office to take one of those 5 CMGC slots. But one of the things we first realized is we haven't done a bridge with CMGC. We also hadn't done a federal highway project with CMGC. So the DOT did not have their CMGC management guidelines approved by Federal Highway. The projects that we had been doing with CMGC were all state funded. So Boyd Tharrington, David Stark, and the team at Alternative Delivery really worked hard with Federal Highways to get that management plan approved. We were able to get it approved. Oops, going the wrong way. And in June of 23, we were able to advertise or send out a letter of interest for contractors to come on board as our CMGC partner on the project. We got really good response with Archer Western Construction, Balfour Beatty, and McLean Contractor as a joint venture, Flatiron and S.J. Hamill as a joint venture, Kiewit Infrastructure, Skanska Southeast USA, and Weber Construction, all submitted letters of interest. And that was in June of 23 when we got the letters of interest in. We shortlisted 3 firms in August and issued a request for qualifications. The middle of August, we had a question and answer session with each of the 3 teams individually, and their statement of qualifications was due August the 30th. And on September the 30th, we're moving fast again, we held individual interviews with each team to discuss the project and their ideas about the project, but also discuss their ideas about CMGC and how they felt about being a partner. You know, because one of the concerns with bringing a partner on, and CMCG in general, when CMCG, the DOT has a contract with the designers, and we have a contract with the with the contractor as our contractor partner. And we can pick the best team of designers in the world. We can pick the best contractor in the world. But if that team can't work together, we're really not doing much. We're not going to have the best project. So we were looking for a CM partner that we thought would fit well with the team and help us move this project forward. So those interviews really helped a lot. Eventually, we selected Skanska USA Civil as our contracting partner. We also brought on HNTB as a CMGC project manager, and that was something that was suggested to us by Alternative Delivery and the Chief's office. You know, and at first I was like, we can handle this here at the division. This shouldn't be a problem. I will admit I was wrong on that idea. We spent the last 2 years heavily involved in this project. I personally would not have had the time to spend on project coordination on the CMGC side as HNTV's project manager did. I think he had to call y'all once a day. I got one call a day from him, and I know he was calling the contractor at least once a day, keeping us all moving, keeping the decisions going forward. So that really helped to blend the team, and it worked really well because the CMGC was new to everybody. Nobody had done a CMGC. Skanska, of course, had, but none of their personnel on this project had been involved in a CMGC project. So once we got the CMGC team up and running, our initial task was to get Skanska up to speed. We had a tremendous amount of meetings. We went back and revisited a lot of the design decisions and talked through, which was good to rehash. You know, we got it all back fresh. And, you know, Skanska asked a lot of questions. They were really careful not to step on any of the design toes and, you know, to make sure that everything went good. And then the other initial task we asked, we said, okay, Skanska, what we really need to know is the baseline of where we're at. Give us an opinion of probable cost based upon this current 90-degree plan set with the 2 foundation options, both of them going deep. So they started working on that. And simultaneously, we had identified, and through talking with Geotech, that we really wanted to do a test pile program so that we could proof out some of the design information that we had, some of the drivability analysis, some of the bearing, and also give our contractor some real good experience on how much level of effort it was going to take, what his production rates were going to be, which we hoped that would help them refine any of their bid estimates. Before we got started with the test pile program, we came in with a first opinion of probable cost based on that 95% or 90% set of plans, and it was $535 million. From Edenton, my office in Edenton, I heard the explosion in Raleigh. I think it was on one of the slides earlier, the STIP estimate at that time was 270 million. And, when we got the 100 million, we worked with Lee Wing, and it was really stressful to try to figure out where we were going to get the rest of the money. Well, now it just bumped up to 535, and it was, needless to say, there was a lot of hand-wringing and a little bit of concern about what to do, because we still had that $100 million grant. You don't want to give it back, but where are you going to get the other 400? So, and right after that, and with that, we started implementing and planning a lot of planning and pricing the test pile program, which included the adding of the additional drilling and testing, which was we hope was going to give us more data about the substance of that middle layer, and whether or not long-term settlement was going to be a problem. So we did all that work, and then we started driving piles in the summer of last summer, May through July. I believe the drilling started earlier. Y'all started closer to January, February. Luckily, we were able to, because the drilling started a little bit earlier, we were able to get back some of the initial test results. With the test pile program, we ordered piles long enough to go all the way to that minus 140. We brought out drills. We were planning on drilling. We were going to see what it was going to take to get a pile to minus 140. Thankfully, some of the compression data testing, and you guys tell me if I'm wrong, I'm not a geotech, had already come back before we actually started driving our first piles, and it was looking like that hanging on the top layer might really be feasible, which means we were dancing in the background because we knew that was going to be much more constructible. So we made changes to the test pile program on the fly. We started driving the initial piles up high. We started hanging them up high, which means if you've ridden by there in the last year, there's some skyscraper of test piles standing up out there, and really testing that top layer. And we ended up driving all the piles pretty high. I think we punched one or two, didn't we, to get a little bit of information on that clay layer to see what kind of setup we were going to get. So then after the test pile program, it got down to, well, what do we know? What did we learn, and what can we do? We're still moving in on, we got the 90% plans out. What kind of changes can we make? Well, changes at this point with CMGC would have been a lot easier if we'd had a contractor on it really early. They had some great ideas about changing span lengths and doing some other things, and we're like, no, we're too far down the road. The economics of reducing the bridge by 1 or 2 spans, it's not worth the time. It's not worth the redesign cost. So some of those ideas we just had to disregard. But we mainly focused on substructure. When we realized we could bear on those upper layers, it reduced the number of piles in the bent. We made a change once we realized we were going to be able to bear on that upper layer, we weren't going to have to drive through hard layers. We made a change to 54-inch cylinder pile in the high-rise bents, the piles that had the biggest load. The division had some really not so great experience trying to drive 54-inch cylinder piles through hard layers. So we were hesitant about using cylinder piles on this project. But once we got to where we knew we were only going to drive to a layer and stop, 54s got a lot more economical in our heads, and then the contractor was able to show us the numbers that they really were a lot more economical, so we were able to cut a lot of the pile out in the mass footings down by going to 54s. Totally, as Andrew said earlier, we took out about 93,000 linear feet of pile, about 335 total less pile in the foundation. With the piles, we made a little bit of change in design when we found out during, trying to keep an eye on your time, we found out during construction of the test pile project, it's a test pile project. We're not driving production piles, so we beat the living pee out of those piles. We really did. We hit them hard, and hit them long. And as a result, one of the things that Tom noticed and Geotech noticed in the PDA data was that our tensile stresses were getting a little high. And as a result, there's a good high chance of cracking a pile when we're hitting them that hard. And so tensile stresses became a concern going into production. We made a change. We increased the pile concrete strength to 10,000 PSI. And through talking with the producer up in Chesapeake, that really wasn't a big cost add. We increased the pull or pre-stress force in every pile. We added a few strands where we could, and that allowed us to get that allowable tensile stress up to 1.2 KSI. I believe we were at 1.0 or 1.1 before. And you'd be surprised that little tenth of a KSI really makes a big difference. Right now, I'll talk to you a little bit about how many pile we've driven so far, but we've been able to stay below that 1.2 pretty easily without having to do a lot of superhuman tricks. The other change we made, and we made one change in the superstructure, and this was actually pretty interesting from a construction standpoint. We had the GFRP in the substructure, which is a glass fiber reinforced something. Most of the substructure bench, if you're a structure guy, structure person, most of the reinforcing in the substructure has bends. Glass fiber, that is the most expensive part of glass fiber reinforcement, is doing the bends, the hooks, the elbow, the 90-degree bars. Through Skanska, talking with the provider, we were able to figure out that if we added a lot of long straight bars to the total reinforcing package, we could get the cost of our GFRP total on the bridge down. Well, where are most of the long straight bars? They're in the deck. Most of our deck steel, longitudinal steel, horizontal steel, it's all straight bars. So we started looking at the idea, or Skanska started looking at the idea of changing the deck to GFRP. And those long, straight GFRP bars ended up being less expensive per foot than a epoxy-coated steel reinforced bar. So we were actually able to save a little bit of money, switch the deck to total non-ferrous reinforcement with the exception of the barrier wall, which will allow, hopefully a little bit more longevity in the deck as well. So that was a real big bonus. Oops. And we went to a full depth slab with the GFRP. The bridge was originally a concrete deck panel bridge with a top layer reinforcing. We had a lot of trouble with high percentages of rejection at a precast plant with deck slabs on the last two big bridges we had with deck slabs. And as a result, we were getting a really overinflated price on the fabrication of those deck slabs. So we did some numbers. A good way of having a contractor on board, he can estimate it on the fly, tell you exactly what the savings is, and it was made the decision to go with a full depth slab versus the deck panels. So with all that, we agreed to all those changes. Skanska agreed to start estimating and trying to get us to a construction agreed price without final plans. Based upon all the changes and a lot of conversation and a really good working relationship that the team had developed in that 18 months. We got limited details from the designers, and Skanska said, well, we feel comfortable enough going ahead and giving you unit prices on a bridge. And in December of this past year, just before Christmas, after several rounds of negotiations, we were able to get the project down to $449,777. Which was still a lot more than the 270, but it was a number that we thought we were happy with. And based on going through all those negotiations, and these are open book negotiations, we're looking at Skanska's numbers, we're looking at DOT, our estimators are having their numbers, and we have the independent cost estimator numbers. So you really learn a lot about where every nickel and dime in this estimate is and where it comes from. We got within all three of us got within 5% of each other of the independent of the three different estimates to get to that 449. Once we got within 5%, we thought we were in pretty good shape, at least to the point that we were going to recommend to the chief's office that we award. I think theoretically, if we took the exit road, kicked Skanska off, we probably could have got a little bit cheaper at bid time. We could have put it out to bid. Somebody would have bid lower, 15% more. They would not have had the knowledge about this project that Skanska did. Skanska estimated this thing half a dozen times, lived it for 18 months. On a normal project, a contractor may get this size, it gets 8 weeks. And so what I'm hoping is, yeah, we might be paying a little bit more up front. We've got a contract that hopefully is not on a ragged edge of profitability from the beginning of day one, to where we're not having arguments about minor changes. And we're really hoping at the end we won't have these really big multi-tens of $1 million foundation claims that we've seen on some other jobs. So as I said, we think we saved about $84.5 million from that initial cost estimate. Date availability was January of 2025. With traffic being done in traffic on the bridge in 28, and having the old bridge tore down in 29. I won't belabor on these. The general area, the biggest thing is we're in a very isolated area. There's not a lot of room to work. There's not a lot of lay down. Delivery of materials is a really big problem. Skanska early on did a kind of a minor coup. If you're familiar with the area, there's a gas station right at the end of the existing Alligator River Bridge, and that's the only gas station in a 40-mile stretch between Columbia and Mans Harbor. And they had a little bit of laydown space, and there's a dredge spoil area down here where they dredged out, and a really nice boat basin. Skanska approached the owners of this property about using it as a laydown area, and they were successful in being able to rent the property from them. So here's a conceptual drawing of where we are, what we're getting ready to do. We are bringing a concrete batch plant on site. Closest batch plant to this project was an hour in each direction. And then if you figure you got an hour of road time plus trying to get it loaded on a barge and get it out there in the middle of the sound, almost 2 miles away, we're going to time out before we get there. So we're going to be producing the concrete on plant, on site. There's 2 work bridges proposed, one here, I'll show you another picture of it in a minute. That's in order to build the vents in the shorter, narrow, shallower water, and the other one is a load-out vent for concrete. Their method of delivery of concrete right now, they've got a Rotec, they've got a work bridge here. We're going to belt feed concrete into these Rotec agitators that can hold 50 yards apiece, and we'll have 2 shuttle barges that can bring concrete out to the pours at one time. One other change that I forgot to mention earlier, on the 36-inch squares, originally we were designing them as voided. Archer was able, in talking with the producer, the voided pile actually costs a little bit more. There's a bigger chance of losing the pile during production, and that little bit of concrete you save doesn't offset the labor it takes to form the void. And Skanska's rigs were big enough to be able to handle the solid pile, the weight of the solid pile, so we switched to solid pile everywhere except for on these trestles, because on the trestles we've got to use the crawler cranes out on the trestles, so we're using a lighter pile out there. This is just a little drawing that we got showing the Rotec delivery system. They'll belt it out into the agitators. The shuttle barges will take it out to pour. Once you get to the pour, we'll have a super slinger belt delivery system on a barge, and it'll belt it into the placement areas. There's a work bridge on the west side. The west side is a little longer as far as shallow water to where before we can float. This is typical 36-inch pile. Skanska is going to have three crane rigs out there, all of which are ringer cranes. Skanska doesn't use, normally in my experience over the years with them, they're not a big spud user on their barge. They normally use a 5-point anchor system and deck winches that allows them to maneuver the barge in really small increments. And with GPS on the barge, we're using a fixed lead system to drive the piles. The lead has the capability of battering left to right, forward and back. And with the deck winches, we can move into position. We're not using any pile templates to drive these piles. The big rush is going to be in the high level. During that, we've only got a moratorium, I think, of about 4 months in the worst part of the year that we can work in that deep channel section. So we've got a 2-week window in July. We're going to drive some 54-inch test piles this July. Matter of fact, we're just working on shop drawings this week. We're going to drive those test piles to get our order lengths, and we're going to try this coming winter, the 4 months of this winter, we're going to bring all 3 pile rigs, crash them together in the high rise, and try to drive all of the cylinder pile this winter. Right now, we started driving pile in February. Right, we've got 25 bents of pile in place. Of the 3 rigs, 2 are on site. One's driving, the other one's doing some demolition of those test piles that we drove over the summer, but pretty soon it's going to come online driving. And then the 3rd rig's coming the 1st of April, where we'll really be banging. Clearing started the 1st of March. We've got most of the Dare County side cleared. The really adventurous part of undercutting through that muck's going to start shortly thereafter. Trestle construction, trestles are being fabricated. We're hoping in early April to have some more cranes on site to start the construction of that, and we're working on yard construction. But, you know, the project has really hit the ground fast. I think a lot of that, the CMGC project process helped that, because we worked together really hard for 18 months before we got to this past January. So by the time we were out in the field working, we were already familiar with each other. There was no learning curve with the contract management team. We'd all been together. And if you work through those 3 price negotiations and come out the other side as still as friends, I feel positive for the rest of the job. Plus, if we do have a cost issue during the life of the job, we know how it's estimated. We have a process in place to estimate that and come to a cost. So I'm a little optimistic, about the CMGC on this project. I think it was a good decision, and I think it's going to be a great project going forward. And that's it for me. And I'm on time.
Are there any questions? We're at time, but if the speakers would like to stick around, any questions, I'll bring the mic out.